Today we are looking at tensor products and matrix representation. So what is the tensor product? Put simply, the tensor product is just a way to build matrices from vectors. It also tells us why when we multiply two compatible matrices, so for example, if we multiplied a 2 by 3 matrix and a 3 by 1 matrix, these two matrices are compatible because these inner dimensions are equal, and so our result will be a 2 by 1 matrix. So if we multiply two compatible matrices, we do the rows of the first matrix multiply the columns of the second matrix. The tensor product actually tells us why we do this. Some other reasons why the tensor product is useful is that it helps us represent matrices in terms of its basis vectors, which might not seem that useful, but it's just a cool thing to know. Express matrices using eigenvectors and understand projections and transformations. Cool. If we go on to look at how we calculate the tensor product, let us have two vectors A, which is going to be A1 and A2, and the other matrix is going to be B, which is going to be B1 and B2. If we were to find the tensor product of these two matrices, we would write the vector A and then circle times, so circle time sign, and then the vector B. This is equal to A1, A2, circle times, and then B1, B2. And in order to work this out, we do A1 multiplied by B1, and that is going to be our first element in our matrix. So A1 times B1 is just A1, B1. Then we do A1 multiplied by B2, which is just A1, B2, and that's our second element. Then we do A2 times B1, which is A2, B1. And finally, we do A2 multiplied by B2, which is just A2, B2. And so from these two vectors, we have created the matrix A1, B1, A1, B2, A2, B1, A2, B2. Cool. If we now let the vector A have n dimensions, so A1, A2, A3, all the way up to AN, and the same with the vector B, so we get B1, B2, B3, all the way up to Bn. If we now found out the tensor product of these two matrices, we would get A1, B1, A1, B2, A1, B3, all the way up to A1 multiplied by Bn, A2 times B1, A2 times B2, A2 times B3, all the way up to A2 times Bn. And hopefully you can just see the pattern. This time it's A3 multiplied by B1, A3 multiplied by B2, A3 multiplied by B3, all the way up to A3 multiplied by Bn. And if we just skip forward, we get An multiplied by B1, An multiplied by B2, An multiplied by B3, and then An multiplied by Bn. So this is sort of our general formula for working out the tensor product of two vectors. So now, with the definition from above, we can write this following rule, I suppose you could call it, where if we have the vector A plus the vector B, and then the tensor product with vector C, it is the exact same as doing the vector A tensor product with the vector C plus vector B tensor product vector C. All this is realistically showing is that the tensor product is distributive over vector addition. If we were now going to prove this, if we first compute what the vector A plus the vector B is going to be, it will simply just be A1 plus B1, A2 plus B2, and then all the way up to AN plus Bn. And now if we take the tensor with the vector c, which is going to be c1, c2, all the way up to cn, we can see that we're going to get a1 plus b1 multiplied by c1, a1 plus b1 multiplied by c2, all the way up to a1 plus b1 multiplied by cn. And so we get this. This we could write in a simple way as ai plus bi multiplied by cj, because that is essentially what this vector is. If we now expand this out, we get ai multiplied by cj plus bi multiplied by cj. And so now ai plus cj is just this tensor product, which is the vector a and then the tensor product with the vector c, and bi multiplied by cj is just this tensor product. So hence why this is the same as this, and that the tensor product is distributive over vector addition. Of course, you could do the longer approach of just working out the left-hand side, working out the right-hand side, and then they will, of course, be equal. Cool, hopefully that makes sense. Moving on with the tensor products of the basis vectors. So the basis vectors are 1, 0 and 0, 1. If I were to take the tensor product of this first vector with itself, we would have 1, 0 circle times 1, 0, which gives us the matrix 1, 0, 0, 0. If I do the first basis vector tensored with the second, I will do 1, 0 circle times 0, 1, and that gives me 0, 1, 0, 0. If I do the second basis vector multiplied by the first, we would get 0, 1 multiplied by 1, 0, which gives us 0, 0, 1, and then 0. And then finally, if we did the second basis vector tensored with itself, we would get 0, 0, 0, and 1. So these are known as the basis matrices. With these basis matrices, we can form or build any matrix that we have. So suppose we had the matrix A, which is A, B, C, D. In order to represent this matrix in terms of the tensor products of the basis vectors, we would have A and then this tensor product, as this is what gives us the first element in the matrix. So we would have E1 and E1, and then we would have B, E1, E2, and then we would have C, E2, E1, and then finally D, E2, E2. So we would have this. So this is how you would represent a matrix in terms of the tensor products of the basis vectors. Moving on from this, we're going to see how the tensor product relates to the dot product. So one thing that we should be able to see instantly is when we find a dot product of our two vectors a and b, that is the same as or equal to the trace of the vector a tensored with the vector b. Just to see that, if we did a1 and then a2 dotted with b1 and b2, we would have a1 b1 plus a2 b2. If we were now to find a tensor product of these two vectors, we would get a1 b1, a1 b2, a2 b1, a2 b2. And so if we now find the trace would just be adding these two elements. We would get a1, b1 plus a2, b2, which is the same as that. So that's sort of an immediate connection. What is a more important connection that we can see is that when we have the tensor product of the vector A and the vector B dotted with the vector C, that is equal to the vector A multiplied by the dot product of the vector B and the vector C. Just to have a look at that, we have already worked out this tensor product over here. So it's just A1, B1, A1, B2, B2, A2, B1, A2, B2. And we will now multiply that with the vector C1, C2, which gives us A1, B1, C1 plus A1, B2, C2, and then A2, B1, C1 plus A2, B2, C2. So that's just me doing row times column. If I now factorize out A1 from the top, we are left behind with B1, C1 plus B2, C2, and if I factorize out A2, we have B1, C1 plus B2, C2. And so I can write this as A1, A2 multiplied by B1, C1 plus B2, C2, as both of these are the same. And hopefully you can see this is just the vector A, and this is our dot product over here. And this is just the dot product between the vector B and the vector C. So the tensor product of two vectors multiplied by the vector C is the same as us dotting the last two vectors and then multiplying it by the vector A. Cool. If we now look at the product of a matrix and a vector, if we now consider a matrix A, which is equal to A1, 1, where the first one, or the first number, represents what row the element is in, and the second number represents what column it's in. We have A1, 1, and then the tensor product between the basis vector E1 plus A1, 2. Cool. So this is just us representing a matrix in terms of the tensor products of its basis vectors. We can write this as a summation where we have I and j, which start at 1 and we sum all the way up to 2, and we have a, I, j, and then the tensor product of ei and ej, where I is the row and j is the column of our matrix. Now, so this is our matrix. If we look at our vector, which is going to be the vector A, we have A1, E1 plus A2, E2, which we can write as a sum where k is equal to 1 all the way up to 2, and we have A, k, and then ek. If we now multiply the matrix with the vector, we can write the two sums multiplying together. So we have this. We can rewrite this taking everything under just one sum. Aij, ak, ei tensored with ej multiplied by ek. This looks very similar to what we had over here. So if we use this rule, we can rewrite this sum as I, j, k as ei, ej dotted with ek. Cool. If we now look at this sum, in particular if we look at this dot product when we have E1 dotted with, let's say, E2, we are getting the vectors 1, 0 dotted with 0, 1. And we can see that's 0. If we had E1 dotted with E1, however, we get 1, 0 dotted with 1, 0, and that gives us 1. So whenever j is equal to k, so whenever these two are the same, we get 1. So 1 if j is equal to k. If we have them differing, we get 0. So 0 if j is not equal to k. As a result, we can write this sum over here as just in terms of ij being 1, and then aij, aj, and then e1. If I now go further and just look at the ith component of this sum, or of this multiplication, we have the matrix A dotted with the vector A and then I is equal to 2j is equal to 1, because I'm taking I out of the sum. I is being determined over here. A, I, J should be no. A, I, J, and then A, J. Of course, the basis vector disappears, as that's simply just timesing by 1. If we now look at this final summation, this is simply showing the row multiplied by column rule, the product of the matrix A multiplied by the vector A. To make this a bit easier to understand, let's use some numbers. So our matrix A is going to be 2, 4, 6, 7, and then our vector A is going to be 6, 2. If we look at what this rule says, so we're going to do A dotted with, multiplied by the vector A, so A multiplied by the vector A, and we're just going to look at the first row. We have the sum of, starting from 1 going all the way up to 2, is A1, A1j, and then AJ. If I wrote this sum out in full, I will get A1, 1, A1 plus A1, 2, A2. So A11 is simply 2, and we're going to multiply this by A1, which is 6, and then A12 is 4, and A2 is 2. And so we get 2 times 6, which is 12, and then plus 8, which is 20. And if we just do this, row times this column, you'll see that we get the same thing. Cool, so hopefully you can see why we do the row times the column whenever we multiply matrices. To look at this further, if we look at the product of two matrices this time, so we'll use the matrix A and the matrix B, we will have the same sums as before, so ij1 going up to 2, aij, ei, and ej, multiplied with k, l is equal to 1 going all the way up to 2, b, k, l, and then ek, and the tensor product with el. Cool. If we now combined these two sums, we will get a, j, k, l, starting from 1 going all the way up to 2, a, I, j, b, k, l, and then ei tensor with ej multiplied by ek tensor with el. So now, if I use this identity, we can rewrite this as ijkl is equal to 1, going all the way up to 2, bk, and then ei tensored with EJ, and then EJ, and then EI tensored with EL, multiplied by EJ dotted with EK. Once again, from before, we can see that when j is equal to k, we will get 1, and for anything else, so when j is not equal to k, we get 0. What that means is we can write this summation as 2ijl is equal to 1, and then aij bjl. So we're just getting rid of the k component using that, multiplied by the basis vectors ei tensored with el. Now, if we read off the il component of this matrix, we get this summation left over, which is aij multiplied by jl, which is again our row multiplied by column rule. Again, just to show this, if we use some numbers, so A is 2, 4, 3, 1, and B is going to be 7, 8, 2, 1. If I want the first row and the second column, I will have sum of 2 j is equal to 1, A 1 j, and then B j 2. So now if I write that out in full, I get A 1 1, B 1 2 plus A 1 2, and then B 2 2. And then finally, A 1 1 is 2. I'm timesing that by B 1 2, which is 8, and then plus A 1 2, which is 4, and then B 2 2, which is 1. So I get 16 plus 4, which is 20 again. So if I were to write out this matrix, the first row, second column, so this element would be 20. And just to check that, in order to get this element, I'll do this first row multiplied by the second column, which is what I did over here. So it must be right. So that's how the tensor product tells us why we do the row times the column when we do matrix multiplication. Going beyond that, the tensor product does become more useful when we look at the projection method, when we try and find the nature of our optimal points when we do optimization, which we will do at a later date. Thank you very much for watching, and hopefully that all made sense.